welcome to the Cosmic Pie Podcast, episode 22, season 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So, Robert, we're trying out something new today.
Trying out several new things, but all focused in one area. So
Exactly. So if you have anything for us, that is comments, or to let us know how things are going, we appreciate the feedback.
Absolutely.
We do have a live chat feature that is running, so if you have any questions or comments, you can use that also.
Mm-hmm.
And you want to go ahead and do our disclaimer.
Okay, our disclaimer. The opinions and beliefs expressed in this show are those of myself and Wayne. They do not in any way reflect the opinions of the University of North Dakota, the Department of Arts and Sciences, College of Arts and Sciences, Department of Physics and Astrophysics. It's just us.
Now, if you like the podcast, don't forget to give us a thumbs up. Subscribe if you haven't subscribed. Say that at the beginning because you never know when people only tune in for, hopefully not, but a fraction of the show, and then they don't get that at the end, right?
Right. Yeah, you never know. I mean, people do things.
Now, we also put up our show on Spotify the next day, so if you're ready to listen to us on Spotify, or better yet, listen to us twice, once now on YouTube, and then again tomorrow on Spotify, because I'm sure you're going to miss something, right?
Right.
Then you have the freedom to do that.
Hey, more views.
We don't count them, do we, Robert?
Yeah, a little bit. just a little bit.
We don't make any money from this, by the way, in case anyone out there is wondering. We are not monetized. We don't want to be monetized. This is free for you. I guess you just got to pay for your internet connection and the power to run your device, but that's about it.
That's about it. And some people might marvel a little bit. Why wouldn't you want to be monetized? Folks, this is through the university. You don't want to even consider the amount of paperwork that would be involved with that.
Yeah, I don't want to even think about it myself, but.
Right.
Okay, Robert, are you ready?
I'm ready. Let's go.
Let's go for the first news item, and this involves something that's going on right now, at least the preparation of such. Now, in the last podcast, a week ago, we mentioned that there is a spacecraft that's due to be launched, and you can see the arrow pointing to it underneath the belly of the L-1011 airplane. It's due to be launched near the Marshall Islands, and on board is a spacecraft that is going to ultimately rendezvous with the Swift Observatory, which is decaying in its orbit because it's interacting with the outer atmosphere as we speak. And it's estimated that sometime, let's say, at the end of the summer or a little bit later than that in early fall, that there's a high probability that spacecraft will re-enter the Earth's atmosphere. Its primary function is a gamma ray detector. That is, it looks for, in particular, what we call gamma ray bursts. So these are these large, sudden increase in a huge number of gamma rays coming from some specific location on the sky. They last typically, a couple seconds, some a little longer than that, some a little shorter than that. And when they were first discovered, which the discovery of them is kind of interesting, it happened back in the 1960s, and it's due to the fact that military satellites, both from the United States and the Soviet Union at the time, were looking for gamma rays coming from nuclear explosions. Now, the Earth's atmosphere blocks the gamma rays, unless they're extremely powerful, that they would evaporate away our atmosphere and bombard us with a lethal dose on the surface. But that would be an object that would be extremely close and produce a powerful, sort of burst of gamma rays beamed in our direction. And people wonder, well, if the atmosphere blocks gamma rays, and what was the point of putting a satellite in space looking down through the atmosphere to see if people were violating the nuclear test ban treaties of the 60s? And what was happening there, what they're good for, is when people were detonating their atomic bombs or nuclear bombs, in the atmosphere, above the surface, not under the surface. Then some of those gamma rays would actually make it upwards to the upper atmosphere, to space, low Earth orbit, and could then be detected. Any nuclear bomb that goes underneath the ground and goes off, those gamma rays are going to be absorbed by all the dirt and rock. So you're not going to be able to detect the gamma rays from nuclear explosions, but certainly have other methods to detect them, like seismometers and things like that.
I was about to say, you're going to detect the earth shaking.
Yeah. So we have other methods, that we employed. Well, in the 60s, when these gamma ray satellites, the detectors, were running, looking down at Earth, they could also detect things that were coming in from the other end, which is out in the space. In fact, what we detected were these bursts that happen in sort of random locations in the sky, and people not knowing, of course, the scientists, what they were, and that information eventually makes it to NASA and other scientists. And then NASA designs specialized satellites to put in orbit to look and study what these gamma ray bursts are. And that was is the primary function of the SWIFT Observatory. And it's been a real workhorse for the last several years. And so it's a shame that this thing is on its way down. And you might think, okay, we'll just build another one and put in the latest, greatest detectors and see where we go from there. But of course, the money's not always available.
Right.
Hence, just look at what happened to NASA last year, for example, and the fight that people had to do to reinstate some of the money that they had lost in their funding. So you never know if the money's going to be there. And the other thing is, if the telescope is working and there's really no issue with it, why not have a way, at least low-cost way, to keep it up there? And that's what this is. This is really an experimental mission of what's called the Link spacecraft to rendezvous with the SWIFT Observatory, grab a hold of it. And it wasn't designed for another spacecraft to dock with it. It's not like it has a docking port on board the observatory. There's robotic arms that will go up to it and grab a hold of it, and hopefully they'll be able to secure a position where the spacecraft will be stable. You don't want the thing all of a sudden tumbling out of control, because therefore you couldn't use probably the SWIFT Observatory, and you may as well decay at that point and through burn up in the Earth's atmosphere. Grab a hold of it, and then once you have it stabilized and pointed in the right direction, then turn on the thrusters of the Link spacecraft to boost the SWIFT Observatory in a higher orbit, one that it would stay up there, several more years before you could also repeat it or just eventually let it burn up in the Earth's atmosphere. So this is really a test in that way. And of course, with tests, you always have delays. So it was supposed to be launched underneath this airplane back on June the 27th, and that was postponed to June 30th. And I was hoping to give everybody like an image of it going into space, the rocket firing. But now it's delayed until early tomorrow morning, our time. So that's on July 1st. So we'll see if that takes place or not. But eventually, hopefully, it could be weather, mechanical issues. I haven't heard what was causing the delay. Usually it's weather in the Marshall Islands. Probably it's not always a good place to be. Who knows? But eventually it'll go up, and hopefully it'll work, and it'll be a big demonstration test of whether this is possible. Because imagine in the future, we could use it to do other things, right? For example, right now the plan in the early 2030s, and that's not really far away from now when you think about it, is to take the International Space Station and dump it in the Pacific Ocean. Mm-hmm. Now, that's a lot of mass. That's a lot of stuff. You can imagine that there's a lot of things on board that space station that, a second glance or second thought, maybe we shouldn't be dumping that in the ocean of the Earth. In fact, there is a group that's responsible for watching over the Earth's oceans in some sense and make a statement when they think something is off, like you're polluting, by the way, the Pacific Ocean. Please give us a list of all the items that are on the International Space Station, like batteries that'll end up being dumped. And are those batteries able to survive the re-entry through the Earth's atmosphere? And if they do, are their casings going to be ruptured so that you have the internal constituency of those batteries spilling out into the ocean? I mean, there's a lot of things you can think of that's not good. So you could solve that problem, of course, by getting hold of that International Space Station and boosting it either into a higher orbit, so therefore maybe it can be used later on. And if you want to really go crazy, and this probably won't happen because it involves a lot of money and effort, why not attach a booster to it that would put it into the sun?
Right.
And then you
that's a lot of energy and effort, though.
It is. So chances are it's going to be, steered on a course that will bring it into the Pacific, just like Skylab and the Mir space
Right.
station and everything else that's come before it. But we should think about maybe we shouldn't be doing this. Maybe after a while, the accumulated pollution is going to have an effect on our planet. Maybe we can do things a little better.
I don't think it's a question of maybe. I think it's a question of, you know, will and desire and saying, yeah, we're going to stop doing this and we're going to do this instead. But, to me, I think it's a waste. Why aren't we salvaging the stuff off of these satellites and platforms? But that takes a whole new set of technology to develop.
Yeah, and I can go one better than that. Why not give it to private business?
Right.
Maybe they have the resources that they could boost into a higher orbit and eventually be like the Hilton. You could spend a couple nights on the International Space Station if you can afford the hotel room cost, and
Right.
and the transportation
And
to
the
get there.
transportation.
But that's going to happen, obviously, right?
It is. Yeah.
Look at
It won't be me, but
look at extreme vacations on the Earth, right? If you have the money, you
yeah.
can go to Antarctica on a vacation,
Mhm.
right? All these sort of exotic places that 100 years ago, no one would ever think of doing that. So, yeah. So Wonder Goon says they should send the ISS out to the lunar orbit and use it as a platform for moon exploration. There you go. Ba-ding.
There you go.
There's a use. Now I know some of the modules probably couldn't stand the boost. For example, the Russian module is sort of on its last legs. There's a lot of air leaks, and one of the things they're thinking about is there's all the strain on the module due to the docking and undocking over the years. So
Right.
maybe part of it can be not used for that, and then the rest of it you could use it. I mean, who knows, right?
Who
But
knows? It's worth considering, though.
yeah,
Um,
is it better or cheaper to design something from scratch, launch it from Earth orbit and pay all that cost, assemble it in Earth orbit and then send it to the moon, or assemble it in lunar orbit to begin with? I mean, that's the trade-off.
right.
So anyways, we'll see if this actually happens tomorrow. If not, and we'll report back next week how things are going with that. Now,
Yep.
speaking about launching things, Robert, the next story we want to share, because we kind of alluded to it last week, was that the Nancy Grace Roman Space Telescope has arrived in Florida at the Kennedy Space Center, due to be
Woo.
launched at the end of August on a Falcon Heavy rocket.
Okay.
Now, this is a big deal. Number one, if it does launch in the end of August, it is several months early. That never really happens. And it's
Yeah.
currently under budget. And that rarely happens as well.
Okay. Wait a minute. Okay, that doesn't happen. So what's going on here?
Robert, you have to make space telescopes great again.
Okay.
Launch them
Yeah.
early, launch them often.
I won't disagree.
Launch them
I would
cheaper.
love that. I would love that. As kind of as we discussed, you want bigger mirrors for the resolution, but at the same time, on Earth, the atmosphere limits you. Why aren't there, any number of smaller aperture space telescopes up there? Sure, you don't get that resolution, but you get outside of the obscuring of the atmosphere, plus the satellites that are getting in the way these days.
Well, it comes down to one word, right? Money, money, money,
Money,
money.
money.
Well, that was many words,
Yeah.
but same word repeated, right?
Right.
You got to have the money to do this. That's the thing. Once, hopefully, with things like Starship from SpaceX, the launch costs will go down to the point
Right.
where it will become a lot cheaper to do this. And so we'll get many more telescopes put up in space. In fact, remember there is a very rich person, him and his wife, who are both of them are rich, obviously. They've already coughed up the money for a private space station, a space telescope to go in space.
Oh, right. Yeah, I remember discussing that.
Yeah.
Yep.
So that's kind of the very first sort of words I've heard on something like this, and they're actually building it now. So it's not like
Okay.
just this lofty idea, but actually are doing it. So we'll see how that goes. So that might be the beginning of this whole cottage industry of privatizing space telescope, putting them up there, and then just, you could, for example, allow somebody to use the telescope, and you just pay the money, right, to use it. They charge so much per second of exposure time, or however you want to divide it up.
Right. I mean, that model works for ground-based. SLU and light buckets work on that model with ground-based telescopes. If you want time, you pay for it.
Yeah,
So
and the good thing about that, you could say, okay, I want to observe at this particular time and get a 10-minute exposure of some faint object. You don't have to worry about the weather ruining it.
yeah,
You just have to worry about mechanical issues or something like that could go wrong, and then they would just give you the time, a different time, right, when things are working. So it could go, for sure.
Yep.
And we'll see that. Now, the Nancy Grace Roman Space Telescope has a nice history. This was the spacecraft that was given by the National Reconnaissance Office to NASA and said, here's a telescope. Do you want it? Because we no longer want it. And obviously, it was built to look down on the Earth, to spy on people. And the size of the telescope is about the same size as the primary mirror in the Hubble Space Telescope. That is 2.4 meters across. And why that is restricted like that is, I think that, and I'm not 100% positive, but the National Reconnaissance Office, the military, remember, had their sights on one of the space shuttles. They were building a space shuttle launch pad in Vandenberg Air Force Base in California. And the idea was that they would launch some of the space shuttle missions that would be purely military out from that base, and then nobody would be around to see it and try to keep it secret what the payloads are and this sort of thing. And if that's the case, then the maximum sort of size of a telescope you can put in the cargo bay of the space shuttle would be the size of the Hubble Space Telescope, so the 2.4 meter diameter primary mirror in this case. Now, the type of telescope that they had built, the Nancy Grace Roman telescope, was of a different F ratio. So they were able to look, even though the mirror size is the same, the curvature of the mirror is different, to the fact that the focal length is not the same as the Hubble. And what it buys you is a much wider field of view. And that makes sense, because the primary purpose is probably not to look at one very small target on the ground, but try to look over a much larger area if you're photographing military installations in somebody's country that might lie north of South Korea, if you know what I'm getting at, this kind of stuff, right? So the beauty of this overall structure is that NASA took this telescope, managed to get the funds to build the instrumentation like cameras and spectroscopes and so on to put on the telescope, refurbish it, and now it's ready to be launched. And it's going to have a field of view that's 100 times greater than the Hubble Space Telescope. So in other words, in one snapshot with the Nancy Grace Roman Space Telescope, you're going to cover an area that's 100 snapshots from the Hubble Space Telescope. So if your idea is to do large surveys, it's
beautiful.
Which is one of the ways that you could use this telescope, which is illustrated in this slide. It's great for that, because you can see such a wide area, and you got to do a lot of coverage if you want to be able to see such a thing. It would take, I never did the calculation, but it would take thousands and thousands and tens of thousands of pointings of the Hubble in order to put together, like a jigsaw or a mosaic pattern, the whole sky. Right? So that would take a long time just to image the complete sky with the Hubble Space Telescope. I should do that calculation. It's easy to do. You know what the field of view is, and you know what the complete coverage of the sky is in terms of square degrees. You can easily estimate with the calculation how long it would take, how many exposures. And it would be years and years and years, right, type of thing, just to survey the sky.
Right.
But, of course, you're 100 times more quickly with the Roman telescope, right, because you can see 100 times the area. So some of the things I had plans to do are 3 main surveys. There's one involving our own home galaxy, the Milky Way. So it's going to do one of these, what they call the galactic bulge survey, to look at the structure not only of the inner part of the Milky Way, but also to look for sources that change. Now, there was a survey that was done way back in the early 1990s, mid-1990s, called the Macho survey. You remember that one?
I do remember that one.
And that was
hearing about it anyway.
Yeah, so that was looking for these massive compact halo objects. And the idea there is that this whole topic of dark matter, and just to kind of summarize that really briefly, is when you look at the motion of stars or gas clouds in the outer reaches of the Milky Way and most other spiral galaxies as well, you find those objects are moving too fast. They're violating the local speed limit. And the way to kind of explain that is that there must be more mass out there, and therefore an additional source of gravity that's causing the motion of these objects in the outer part of the galaxy to be a lot faster than what they should be. Now, some of these objects, people had proposed different, things. Are they black holes? Are they, some type of subatomic particle? Or maybe it's ordinary things. There's just a lot of them. And what are the ordinary things? Well, things like white dwarfs. Maybe there's planets all over the place, rogue planets that are not associated with a given star. They're just sort of in orbit around the center of the Milky Way. And you have enough of these things, quadrillions and quadrillions of them, all their mass added together would make up the dark matter sort of idea. It would give rise to the fast motion of these objects in the outer part of the Milky Way itself. So all these ideas were proposed, and this Macho survey was looking then at different parts of the Milky Way to see if they would detect some of these objects. And it's interesting, the tool of detection. Do you remember, Robert, how that Macho survey worked?
I honestly, I can't say that I do. Like I said, I remember it being mentioned. I remember it being done. But I also mentioned I didn't know that much about cosmology at the time, and was one of those who kind of scoffed at the idea of dark matter. So
it was the gravitational lensing. The fact that, remember, if you have like a faint object that you can't see directly, if it passes in front of a star that you can see, when the alignment is right, it will cause a magnitude increase in the brightness of the star that you can see. So all of a sudden you watch a star and it increases in brightness dramatically, and then it fades out again over time. And
something passed in front of it.
Exactly. If that brightness change in a certain specific way, then you can then estimate what is the mass of that object that passed in front of it, the foreground object. And if these events happen a lot, then you can get an idea of the density, how many of these objects are out there orbiting around the center of the Milky Way. Now, they did find some objects. A lot of them had a mass of roughly a half a solar mass, so that's more consistent with the white dwarf scenario. But there's not enough of them. The density is way too low to explain that flat rotation curve, the motion of the stars in the outer part of the Milky Way. So we know that the dark matter is not made up of these objects.
Well, it's also too little to make up for like the motion of the bullet cluster of galaxies and things like that too, right?
Yeah, all the other evidence that we have for the presence of dark matter just doesn't work.
Right.
So that's what this survey is, to do a little bit of that. The other one is to look away from the galaxy, the plane of the Milky Way, so look above and below, and therefore you can look at high redshift stuff. So this is the high latitude, as they call it, wide area survey, and also the high latitude time domain survey. So looking for brightness changes of various objects as well, but looking away from the plane of the Milky Way. And the reason why, if you want to look at galaxies, if you look at near the plane of the Milky Way, think of a pancake-like structure, and you're looking at it edge on in space. Well, you can't look through that pancake because the interstellar gas and dust that's in our galaxy blocks the view of background objects. So you want to look in the other direction, above and below the plane of that pancake, and you get a much clearer view of what's out there in deep space. So that's what they're going to utilize the Roman Space Telescope to do initially, then, is these sort of three main surveys. So what will we have? Well, we'll have the Roman Space Telescope, the Hubble Space Telescope is still operating, and of course we have the James Webb Space Telescopes that are out there, and plus other telescopes that are observing in other parts of the electromagnetic spectrum that are not optical in nature. So these are three sort of main observatories that can observe at optical wavelengths and in the infrared as well. So it's going to be interesting. That'll be kind of cool to see that.
Right.
Now, speaking about our galaxy, there is another telescope that's out there making observations now. This is at the L2 position. So you want to describe again for those maybe who weren't familiar with that? What do we mean by the L2 position?
Oh, okay. Yeah. L refers to Lagrange points. And essentially these are spots where, like, the Earth and Moon's gravitational forces balance out, or Earth and Sun, or Earth, Moon, and Sun in some cases. And so L2, I think, is Earth trailing, or is it Earth leading?
It's behind, remember, the Earth
Oh,
relative to the sun.
yeah. Okay.
Yeah.
Yeah. So, these are just points where the gravity balances out, so objects can sit there, or actually, in most cases, they orbit the point, because there's only a couple of them that are actually points. Most of them are areas, regions. So we refer to them still as Lagrange points, or L points, but
Yeah, that's a misnomer, right? So
yeah.
but there are a lot of vehicles that are there, spacecraft. The James Webb spacecraft is there, and there are lots of other
Yeah.
ones that are there as well. And so the Euclid Space Telescope, which was built by the European Space Agency, is also at that position. So it's a telescope that can observe at optical wavelengths. It has a mirror. It's about 1.4 meters in diameter. It was put up by an unmanned rocket. It wasn't put up by the space shuttle or anything. And it's actively working now. And so the image that you see on the slide is towards the center region of our Milky Way to get sort of a perspective what the part of the bulge looks like. And I'll show you a better slide here in a second. But in this one image, this is an optical image, you can see evidence for gas and dust. In fact, you see the dark splotches everywhere. That's due to the absorption of light of objects that lie behind due to dust. So it's the presence of dust. And what you see in this one image are over 60 million stars in just this one small section of the Milky Way towards the center region.
Yep.
So it's amazing when you think about how much is actually out there, right, in our galaxy. Well, our galaxy alone, estimated hundreds of billions of stars, maybe even 200 billion, depending on their average masses and so on. So
Right.
there is a lot of stars, and just our galaxy. And in our whole universe that we can see, it's estimated to be at least 1 trillion galaxies with those billions and billions of stars, right? That's where Carl Sagan, remember the term billions and billions, right?
Which he never actually said.
No, but he was made fun of it.
Yeah,
He took the heat for it, put it that way.
he did. He did.
But that's where that came from. The fact is literally, there are trillions and trillions of stars in the observable universe.
Yep.
So they say there's more stars in our universe than grains of sand on all the beaches of the earth.
Mm-hmm.
By far. And of course, what I wonder, who went around counted all those grains of sand on the Earth's beaches anyways?
And the answer is we probably did the same thing as we do when we're counting stars. It's statistical counting methods. You look at a patch of sky that's of known size and you count all the stars in it. Then you go to an identical size patch somewhere else, count all the stars in it. You count up a bunch of patches, average the number of stars. How many patches of that size do you have in the sky? You got the number of stars.
Now, that's easy. I was going to get a graduate student to count all that.
Oh, yeah. I think you need lots of graduate students.
Unless you get one who's going to be there a while.
Yeah. Like, a few million years. And although graduate school feels like that.
You got to get out and work at some point and earn real money.
Right?
Now, just to give you an idea of some of the work that this Euclid Space Telescope is doing, on this slide, you get a sort of idea of some of the objects. For example, at the bottom, it's going to look at interstellar nebula. Some of them, very dusty, so obscuring nebula, emission nebula, star clusters, the region towards the galactic bulge, as we showed you on the previous slide. And on the top panel, you get an idea of sort of the edge on what looks like the Milky Way, what we think it looks like. And the distinctive thing you see there is not a flat pancake. It's actually warped on the ends.
Mm-hmm.
Now, Robert, I'm going to ask
Yes.
you this question. Why would the disk of the Milky Way be warped? What do you think would cause that?
Oh, gravitational interaction with another galaxy. That's the only thing with enough mass to pull that trick off.
And what would be those other galaxies?
Probably right now would be the large and small Magellanic Clouds, but who knows what was around in the past?
Yes, exactly. And the Magellanic Clouds, they have the large Magellanic Cloud has about 100 times more mass than the average low mass satellite or dwarf galaxy that's in orbit of the Milky Way. So they would be the ones that do the perturbing the most
Right.
gravitationally. So yeah, that's what we think is going on, is the perturbation from gravitational tidal forces ultimately give rise to the warpage of the disk of the
Yeah.
Milky Way. But it's
And
observable, right? You can see it.
yeah.
You know.
And and it'll be nothing compared to, a few billion years from now when Andromeda and the Milky Way start getting close together. I'm looking forward to it. I really want to see it.
Yeah, so that's people often
Sorry.
wonder. Well, I'm just thinking ahead. It's like the paper that we talked about last podcast, where using different models, it looks like the sun, when it expands to its maximum size throughout its evolution, it will not quite reach the orbit of the Earth, just shy of that.
Yeah.
Where prior other models have shown that no, it will just reach the orbit of the Earth, so the Earth will be incinerated. And so there's this like uncertainty, the kind of like which is it going to be, depends on what models you use and how sophisticated they are and so on and so forth. So we don't really know. It's hard to judge, right on that knife edge of knowing
Right.
one way or the other. And that's the same way with the Andromeda Galaxy and the Milky Way. So when we look at the Andromeda Galaxy, we measure its spectra. We see all the spectral lines are all shifted to the blue, which tells us in terms of relative motion that we are moving towards each other. Now, the thing is, will we have a direct collision? Well, if you see something in the far distance, and right now the Andromeda Galaxy is 2.5 million light years away, which is interesting from the point of view is if you go outside at night in a dark location, look up in the constellation Andromeda, if you know exactly where to look, you can see a faint fuzzy object. And that is the light, and that's the light from that galaxy. And that light that enters your eyes at that moment left that object 2.5 million years ago.
Yep.
Robert, that's even before I was born. That's so long ago. Now,
I wish.
now.
Oh, wait, that's how old I feel. Never mind.
My bones feel like that old.
Right.
Especially when you get up in the morning before you get going, right?
Yeah.
Now the thing is that it's going to be a while before that galaxy and the Milky Way touch each other. So is there any sideways motion? Because if there's sideways motion, then maybe it'll miss us completely. It kind of go by us, miss us, go out a certain distance, if not escape altogether, and then maybe turn around and then we go towards each other again, and then there's a collision, or maybe we miss each other. So all of it depends on the exact trajectory that we will take.
Right.
So how do you know then what is going to be the path over the next 4.5 billion years, which is estimated time in which we're going to collide? Is you look for sideways motion. And how do you look for sideways motion? Well, you use the best, highest resolution observations that you can have and also space them apart as long as you can in terms of time. So one of the things you could use is the Hubble Space Telescope. That has very high resolution because it's in above the Earth's atmosphere. And you can look at images taken of the Andromeda very early on when Hubble was first launched and compare them images to what you take of Andromeda today. So you space them out for several decades and see if you see any sideways motion. And right now, as far as the research that I've seen, there is no sideways motion.
Oh.
But some people argue that there may be. It's kind of buried in the uncertainty. And of course, it depends on the fine grain analysis that you do, trying to extract as much high resolution signal as you can from pixelated data. So if you had to put money on it right now, I would put money on the fact that we will collide. But that result could change with better observations in the future. In fact, some of these 30-meter class telescopes, like the 39-meter telescopes being built by the Europeans right now, the European Southern Observatory in Chile, it will have a much higher resolution than even the Hubble Space Telescope because it has a much larger mirror. Even though it looks through the blurring effect of Earth's atmosphere, it will have adaptive optic system running, and given the mirror size, it will be higher resolution than the Hubble. So it's, future observations like that over the next maybe 50 to 100 years that will probably allow us to figure out for sure whether or not the two galaxies will be colliding. And as you alluded to already, that's going to be a real mess when and if that happens.
Yep.
So,
I mean, I enjoyed one show I saw. I don't even remember which show on that very topic, and they got into the point that the two best options for Earth to happen. Now, granted, this is 4 billion years, so the sun's dying at that point anyway. But the two best options for Earth will either be flung into the supermassive black hole at the center of one or the other, or will be thrown out into these tidal tails, as they're called, where stars are just stripped away by the massive gravitational forces involved and thrown out into intergalactic space. So, yeah.
Now, Extra Buller has a question.
Okay.
When you say Andromeda is 2.5 million light years away, are you talking about from Earth to Andromeda's closest edge, or from the closest edge of both galaxies, or something else? The answer is yes. The size of the Andromeda compared to 2.5 million light years away, it's like a way to think about it. It's like saying, what's the distance from where we are right now, Grand Forks, North Dakota, to New York City? It doesn't matter if you're measuring from the Statue of Liberty, which is, in the harbor area, or you're measuring from Times Square, or you're measuring from the edge of the city closest to us. Given the size of the extent of the city compared to how far away we are from New York, it's irrelevant.
Yeah.
So we don't make that distinction because it's just so small compared to the distance between us and Andromeda.
I mean, could we?
You could.
Almost certainly.
You could.
But, it's like being in San Diego and ask, how far away is that car? Well, are you measuring from the front end or the back end?
Yeah. Now, if you're a stickler for details and you want to know, it's like, how do we measure the distance to the Andromeda galaxy? And historically, it was Cepheid variable stars. And then when Hubble did that like 100 years ago, back in 1926. Right. And so you can just see, okay, where is that Cepheid star? Is it on the edge closest to us? Is it a little bit further? Is it on the backside of Andromeda relative to us, and so on? And therefore, you can make that distinction of what is this distance and how is it calculated? But on average, given how far away the galaxy is, it's very minute extent of it compared to 2.5 million light years. But you could make that number. So,
yep.
Okay. So the next one I wanted to talk about, and it's news that just came out today. So this is breaking news, Robert. Breaking news.
What's it breaking? Wait.
Breaking news. It is breaking the news streams out there because we have a new story, that news item that just came out, a new one. And it's finally, after many, many months, the LSST, which now, because it initially stood for Large Synodic Survey Telescope, was changed because the telescope, which is the one down in the southern hemisphere in Chile, it is about 8.4 meters in diameter, and it's designed to do an all-sky survey every 3 nights. It'll image the southern sky. Right. They renamed that telescope, the observatory, as the Rubin Observatory, and then they changed LSST to now mean Legacy Survey of Space and Time. Now, for the last several months, this telescope was undergoing commissioning, working all the bugs out of the system, and it's a very complicated type of telescope, so there's lots of things you need to tweak, lots of dials you need to turn, and it's finally announced today that the main survey has now begun. So as soon as it's nightfall in Chile, which is coming up right around now because it is now winter time in Chile, so it gets dark early, local time, the survey is officially beginning. And this is a 10-year survey to keep mapping the southern sky every 3 nights and stacking those images together to not only look deeper and deeper and deeper as you observe more and more, but also to compare to see how things change from one image of one location of the sky to when it was observed, let's say 3 or 4 nights later, to look for things that move or change in brightness, like asteroids and comets and variable stars, and you name it, all kinds of things that you can think of.
Right. And I'm looking forward. One thing I hope they start finding, and I think I saw something where somebody has is let's see objects out moving in the Oort cloud, because right now we've never actually seen anything moving in the Oort cloud. We see comets coming in that from their trajectory and everything, they clearly came from there. But it'd be nice to see, look, there's one. And when you're doing that sort of thing, you'll pick up little slowly moving objects like that.
Well, then don't forget Comet 3I Atlas.
Right. We'll see more of them coming in.
Look at all the hoopla associated with that, right?
Right.
So we're going to see a lot more of those type of objects that came in from beyond our solar system, made its close approach to the sun, and then went off again. A lot of these objects I'm sure we've missed because we're not looking over large areas of the sky, so they're easy to miss. So what we can do in this case is, because we're looking at things changing in position, we'll be able to better detect these sort of things. So look out. You're going to see a lot more detection of these interstellar objects, whether they're comets or asteroids, or maybe something else.
Maybe a planet. That would be kind of neat.
I was thinking of something else, like, artificial.
Oh.
So if there's any chance at all of any type of probe that has been visiting the inner part of our star system here, that if we see it moving, this telescope will be designed, can detect such a thing.
Right.
And so who knows what we detect? Of course, now I just open up the door for all kinds of stuff, right? But, some people would say, that object I seen streaking through the atmosphere last night that everybody says it was a meteor, how do you know it was a meteor unless you actually find it laying on the ground and can make that connection to the phenomena you just witnessed the prior evening? You get a lot of that, but I mean, there's, we can't say exactly what fell, but it had all of the characteristics of a meteor.
Yeah.
So, and when you find it, it would be a meteorite, not a meteor wrong. You see how that works?
Here's hoping. But at the same time, most of them detonate in the air because they turn into big balls of plasma, which is why most craters are round. You don't get a sliding hit, you get a boom.
And you get a lot more of that lately because everybody's got those cameras,
ring cameras and things like that.
Yeah, so you get a lot more, which is interesting. But so this survey is going to look at everything from near space. You're going to see satellites going by like crazy. So one of the things the processing, the software that's used to analyze the images would be to get rid of those streaks caused by all the satellites.
Yes.
Starlink. Think of Starlink, right? Those and other ones as well. And you can observe all the way out to basically the observable edge of the universe, because you'll be looking at objects that are really far away and trying to get evidence for be able to characterize, the influence of dark energy on the expansion of our universe, which we've talked about in previous podcasts, and also for evidence of dark matter and how that permeates over large areas. So you could write a huge book on all the potential discoveries that can be made with a telescope like this.
Yep.
So we'll see. And if you want to do any better than this, number one, put it in space.
Mm-hmm.
Number two, build a larger telescope so you can see fainter.
Let's put a 30-meter telescope in space.
That's what I mean. And that's going to happen.
It will happen sooner or later.
Yeah. Right now it would cost a heck of a lot of money.
Right.
So you better win the Powerball many times over.
Yeah, not just once or twice.
Many times over. But it will happen eventually.
It'd be easier to put up, a 10 1-meter telescopes over several kilometers and do a space interferometer than it would be to do a 30-meter single mirror.
And there you get the high resolution, but you wouldn't get the light gathering ability. You wouldn't see as faint, but you get the de facto resolution that a large mirror would put up.
Right.
So there are different tricks that you can do. It's just a matter of the advancement of technology to hopefully make things cheaper, including getting things into space, and also having the resources, which means having the population of a certain country all agree that's worth doing.
Yeah. And you say a certain country. Some of these things would take everybody. everywhere getting involved.
Yeah,
They
but
really
the
would.
people, those countries, they need to agree with this, right? They need
Absolutely.
to think it's worthy to spend money on this kind of stuff.
Yep.
So that's the thing we're looking for, obviously, stuff like that. Okay, to kind of switch gears a little bit. So you know the saying, see you later, alligator?
Yeah.
So now it's see you later, accelerator.
Accelerator.
And the reason why that's there, I never came up with that statement, by the way. So
Okay.
I got that off the internets, as George Bush would
So,
say.
so you don't need a penny every time somebody says it?
No.
Okay.
So the Large Hadron Collider, and so do you want to say what that is and maybe the history of what it actually discovered a few years back?
Well, a few years back, it discovered this thing called the Higgs boson, which is bosons, if I'm remembering correctly, are the particles that transmit forces like gravity or electromagnetism, the weak force, the strong nuclear force. And bottom line, it was hypothesized because why do things have mass? And the bottom line, the Higgs boson is this idea or this particle that gets exchanged through this field called the Higgs field. How it all works, I don't know. I don't understand manifold theory and all of this quantum chromodynamics. All of this stuff is beyond my pay grade. But bottom line, the Large Hadron Collider was due to the way electromagnetism and charged particles and forces on them work. You need a massive circle, a massive ring to accelerate stuff to high speeds. So in the case of the Large Hadron Collider, it's kilometers wide, I think.
Yeah.
And it's able to get something like a proton or an electron up to really close to the speed of light. And you got two streams going in opposite directions, and at some point you shift the magnets a little bit and make them meet. And out of that collision, it makes a train wreck look like a walk through the park. So a lot of stuff starts splattering and dripping out.
Okay, can I correct you now on all this?
Absolutely. Please do.
I'm thinking particle physics is just like, oh,
yeah,
groaning. So first of all, the biggest thing was, as you mentioned, the discovery of the Higgs boson. And this was on July the 4th.
Oh, I didn't remember that. Cool.
2012.
Okay.
And that's what it was designed for. So the collider collides, as you mentioned, particles. In this case, the name Large Hadron. Hadron includes things like protons. Mm-hmm. So it's actually two proton beams that circulate in opposite direction. As you mentioned, they are brought to collide at a certain point, right? Once they get ramped up to a very high rate of speed, close to the speed of light. And the faster they go, the more kinetic energy they have. So the more energy of the collision when they collide. And you need to bend the beam. These are positively charged particles, so you can use magnets to deflect their paths. So you need very strong magnets in order to beam them in a circular pattern that's small enough that you can actually build it using the pre-existing tunnel that was there in Europe at CERN.
Right.
So the Higgs themselves are not force carriers. For gravity, be the graviton.
Right?
Oh,
fair. Right.
Yeah. And for the electromagnetic force, it's the photon. But you were right in that the interaction of the Higgs field, as we say, with particles, I guess that's one way of thinking about it, that interaction then gives you the illusion of mass, of inertia. If a particle doesn't interact with the Higgs field, then it has no inertia in that sense, no mass. And so that's when we talk about massless particles. So there are some particles that interact with the Higgs field, some that don't. And the ones that do then are the ones that we give a mass number to it.
Right.
That's a very simplified way of thinking about it. It's much more complicated than that, but that's good enough. So the thing that's interesting is, in colliders in general, have been around for a long time, colliders.
Mm-hmm.
And someone once said that it's like taking two watches, and these are not digital, but the old mechanical watches, slamming them together, and then looking at the parts that fly out of the collision to get an idea of how those watches work without opening up the watch to begin with. So you see all the gears and springs go flying and try to piece together then how they work. But that's not exactly a good analogy. All analogies break down at some point. Because in these collisions, it's not like pre-existing things inside of protons, in this case, come flying out. It's just that new things are made from the energy of the collision.
E equals mc squared, folks.
Exactly.
Energy and mass are kind of the same thing.
It's like taking two pieces of chalk, slamming in together, and refrigerators and cars go flying out. You make something totally new and different that never existed prior to the collision.
Right.
And so the more energy you have in these collisions, the more things that you can create of higher and higher mass. And one of the major theoretical understanding that we got to understand the particle physics is known as the Standard Model. And we're looking for something that goes beyond the Standard Model. The Higgs was predicted. It is part of the Standard Model. So then when it was discovered, it was like a great relief. It should have been there if we're on the right track with the Standard Model. But another point of view is it was boring because we knew it should have been there. Yeah, we found it. But let's find something that shouldn't be there. Because that's how...
Or that we didn't know would be there.
Yes. So then we have to change our theoretical understanding of things. And that's how a lot of progress is made in science, from something new.
Yeah.
And unfortunately, we haven't found anything new. And one of the new things we're looking for are these supersymmetric particles. Now, not to get into it, but a lot of these ideas that we have that tries to unite all forces of nature, things like people might have heard about, like string theory, they relied on the existence of supersymmetry, which means that there should be a whole zoo of particles that exist out there that haven't been seen yet. So for every particle you could think of, like the photon, there would be a supersymmetric particle called the photino, and so on and so forth. And a lot of these supersymmetric particles should have been made in the energy available in the collisions of the Large Hadron Collider up till this point today. And they haven't been made. They're not there.
Right.
And most, if not all, theoretical physicists are saying that supersymmetry probably doesn't exist, at least not in the form we thought it would.
Right.
So a lot of people are going back to the drawing board trying to understand that. And of course, there are ways of hiding these particles. You can make them more massive, so you need more energy of collisions to create them. A lot of people don't like that because it's like, well, no, that guy kind of go against the, if you like, construction of this theory early on, where they didn't think they would be that massive and shouldn't be that massive. So now you're sort of ad hoc changing the rules of the game.
Right.
One way to find out is to make more energetic collisions. And so what's happening with the Large Hadron Collider is they've shut it down now, and it is expected to turn back on in 2030. So it's going to be down for essentially 4 years. And when it turns back on, it should have about 100 times the luminosity as what it has today.
Wow.
Now, luminosity and particle physics collider science is similar to what we meet in astronomy as luminosity. In astronomy, luminosity refers to the total amount of energy that's radiated per second from some object in all directions, like a star. Mm-hmm. So what they mean here is the amount of energy then per second that's created in the collisions of created in the collisions of these particles. And the more particle collisions that occur per second, the higher the luminosity. And it's with, huge number of these collisions that eventually you can create one of these rare type objects. Let's say a certain object, a certain particle you're looking for is only created every 10 billion collisions statistically on average. So you'd have to collide or go through 10 billion collisions before you have a good chance of finding one particle that you're looking for. So clearly, if you have trillions and trillions of collisions happening per second, that ups your chance of finding that particle. So there is a huge benefit of having this higher luminosity for the collider. So people are hoping, of course, something new will be discovered once we run at this much higher luminosity.
And that brings up something Extrabula asked about, which is, yes, there is a proposal to make an even larger collider, but it's meeting a lot of resistance because people are going exactly like we've stated. What is there to gain? What you were looking for, what you said would be there, isn't there. Why should we pay for something bigger that you're ad hoc adding on? Oh, it might be here instead.
And the thing that people will go to right away, priority number one, is dark matter.
Right.
If dark matter is some type of subatomic particle, it is an add-on. It is outside of the standard model of particle physics. So maybe in these collisions, we will find the dark matter particle. We will create it. And many of them, of these high energies that we attain. If we don't create it, then it must be at even higher mass than what we think. And we need even more energy, which means you need a larger collider that you can't modify this one to match, and therefore you have to build something new. So that's the biggest selling point right now, is the dark matter issue.
Right. But again, you've got to have, for the outlay that this will take and resources. I'm not going to talk in terms of money. I'm just talking the resources that go into it. I will have to side with the people who say, show me. Why do you think it's there? Because we can go, well, maybe it's there all day long. Show me,
Well, it comes back to that word again. It starts with an M and rhymes with honey.
Right.
That's what it really comes down to. Now, one of the earlier sort of candidates for dark matter, Robert, was the neutrino.
The neutrino. Yeah.
And now neutrinos, and it turned out that they do have a little bit of mass, right? And we can calculate how many are out there, and it doesn't make up enough of the dark matter. So it's not in the form of neutrinos. But people were hoping that this would be, and neutrinos are interesting because if they have so little mass, they don't interact with anything else, just only through gravity. It's like the perfect almost candidate that you would need for a dark matter particle. Right. But unfortunately, there's not enough of them. But people, there's lots of stuff going on with neutrinos. You like to understand their properties a lot better than what we do today. And there are different experiments that are either planning to run or in running now to detect neutrinos. And one of these experiments is known as IceCube.
Yes, I've heard of it.
Right. So what you do is you go to Antarctica and you drill down using heat to melt the ice. And you put in a long string of photomultiplier tubes, and then you let it freeze over. And it turns out that the ice, when you go down under, is extremely transparent. And you have these strings, if you can envision that, down in all these different locations. So just hanging there almost like, like a fishing line with a weight on the end. Yeah. Waiting for neutrinos to pass through the Earth and ultimately to go through the ice nearby. And because they're passing through a substance, they can travel faster, if they're high enough energy, faster than the speed of light in that substance. Not faster than the speed of light in a vacuum of space, but faster than the speed of light in the ice, for example. And when you do that, you release Cherenkov radiation, this blue light. And that blue light can be detected by these photomultiplier tubes, these light-sensitive devices. And this experiment has been running for a few years now. And one of the things it discovered a couple of years back was an extremely high energy neutrino. And we're talking about penta electron volts, 1,000 trillion electron volt energies.
That's crazy.
And
that is insane.
The insane part is, what the heck no, it's not on Earth, it's in our universe, that would create such a high energy neutrino. And people have been looking around and looking around and looking around. And what has been released recently, a study that was done saying they think they have the candidate, the culprit. It's known as the Shadow Blaster Galaxy. This galaxy is 11 billion light years away, and it has all the characteristics that it could potentially produce these type of high energy neutrinos. And they were different observations that were done with the Gemini telescope, the ALMA submillimeter array, and so on, that shows that this candidate galaxy may be the one. And if you look in the image in the middle, and then even on the right panel, you'll see the lensing effect that's occurring here. But the characteristics given a spectral energy distribution and what we see in terms of the energy output, that it could potentially be the source of these high-energy neutrinos that the IceCube experiment has detected, which is really interesting. And that tells us that these neutrinos then are definitely cosmological in origin. They are not nearby, folks. They are far, far away.
Well,
but that story is still open-ended. We'll see how that develops in the near future.
I mean, PEVs, the Large Hadron Collider is still in the GeV range, I think.
No, thousands of electron volts.
Okay.
Yeah, so it's at in the beginning it's up to about 13 TeV is the energy.
Okay. So, but this is, like, let me get 1,000 times bigger than that.
Yeah.
And neutrinos have a lot less mass than a proton. And we're already getting protons up to nearly speed of light. So this thing was moving.
So
Holy cow.
the current, when you get just to be clear, the Large Hadron Collider has two beams moving in opposite direction. The maximum energy per beam is 6.8 TeV.
Okay.
And when they collide, that's a total collision energy of 13.6 TeV.
Yeah.
So this is essentially, almost over 100 times more energy than that.
Yeah. Wow.
So it's amazing when you think, but just to be able to find an object that kind of looks like a candidate of the source of these high energy neutrinos, I think that's pretty cool when you think about it.
Yeah.
So
it is.
Now, Robert, this is the season, at least in this hemisphere, of fairs, and exhibitions, and so on. And what's your favorite item you like to eat when you go to a fair?
Funnel cake.
Cotton candy, Robert.
Oh, right. Yeah.
Cotton candy. Well, we found the source of cotton candy. You always wondered where cotton candy comes from, didn't you?
No, not really. I've kind of figured it out when I was pretty young and watched them twirl the tube in the little pit. So
they should hide that so nobody knows where it comes from.
I agree.
They just hand you a bag of cotton candy and said, "Here."
Yeah, here, it's magic.
Now, the cotton candy planets are observations that were done with the TESS spacecraft, right, which is the NASA spacecraft that's looking using the transit method to look for extrasolar planets going around other stars, by using the fact that the light from the star will dim periodically due to the planets moving in front of the star relative to our location.
Right.
Now, this particular star, which is known as TOI-291, how could we not forget that label, right? This star is estimated to be about 1,110 light years from us, and two of its planets, they estimate, due to the change in the light as it orbits the star, so we call that change in light with time the light curve. The light curve tells us that each of these planets are about the size of Jupiter. That's not a big deal. We see lots of that. Lots of candidate exoplanets are that size. But the estimated mass of these planets, which we get from the orbital motion of the planets, so it's basically Kepler's third law, period squared goes like the semi-major axis cubed, we can get an estimate of the mass of these planets. Now, here's the interesting thing. With the size and the mass of these planets, we have the density. When they calculate the density of these two planets, they get a value, get this, of approximately, it's about the same for each one, 0.04 grams per cubic centimeter. the density of cotton candy.
Cotton candy. Wow. I was just trying to put it in my head, and I'm sitting here like, I didn't jump immediately to cotton candy. I started thinking, that's about the density of like Mars's atmosphere or something, or cirrus clouds here on Earth. So that's kind of insane.
Can you imagine planet size of Jupiter having such a low density? Is there any rocky core to it at all? Like, would it be
I can't see how there would be.
an asteroid size core?
Yeah.
Maybe? It
Right.
would be so small.
Oh,
And how could that planet hold on to that atmosphere?
right. That's my next question. Then the next question after that is, how close are these planets to that star?
Yeah.
Because for it to puff out like that and get that low density, I would have to imagine it's getting some pretty serious energy input from somewhere,
And couldn't it
some heating. So
imagine
I
it
have
could,
to wonder if it's close to the star.
and then how stable are they, these planets, right? Are they going to be
Right.
being torn apart? Because you can easily strip away its atmosphere at that.
There you go.
Amazing when you think
Yeah.
about it. But what it really is, so they're not plasma, no, so they wouldn't be expected to be hot. So
Okay.
you
Well,
need-
in that case, that rules out that is.
yeah, but
How
I'd have
would
to
they
double
not
check on that how
collapsed?
close they are. But yeah, I don't
I mean,
believe they're
one of them.
I don't believe they're close enough to the host star to be hot enough to be plasma. And of course, if
Interesting.
they're extremely close and hot, then they would evaporate away, right?
Right.
Those particles that make
point.
up the atmosphere would gain enough kinetic energy to just move away from the planet.
Right.
And so it would evaporate away, essentially. Very interesting. What it really tells us, I think, is our solar system is not, I mean, people initially thought before the discovery of planets in the mid-90s that any solar system out there would probably be like our own, right? You have a few rocky planets and then the giant planets, and you probably have asteroids and comets. It just modeled after that because we are heavily biased because we knew of only one solar system, our
Sample
own.
size of one.
Yeah. And what we're seeing now, we've got literally thousands and thousands and thousands of planets, exoplanets that have been detected, is that of the solar system that we can characterize fairly accurately, they're nothing like our own solar system.
Right.
In other words, these solar systems come in a variety of flavors, and the number of flavors is huge. It's not small.
That said, we have found a few that are like our own.
But most are
But
not,
most are not. They're nothing like our solar system.
which really tells you that if you're modeling the formation of a solar system, you probably don't need to have your parameters constrained to the point where you have to produce a solar system like ours, that you can open up that parameter space and that
Yeah.
different planetary systems come in a huge variety of forms and shapes. That's what that really is telling you.
Right. I mean, I'm sitting here going, because planet formation was what got me into astronomy. And I remember when, it takes about a billion years to form planets. Then we started finding stars with these protoplanetary disks around them and started looking at other young stars and realizing that all the gas and debris is gone by the time the star is like less than 200 million years old. You don't have a billion years to form planets. You have like 100. Holy cow. That changed thinking right there, because that's a blink in the eye compared to a billion. It's a
Yeah.
long time to us, but it's nothing compared to a billion.
Yeah. So we certainly have a lot of work to do and to try to understand fully what goes on in planetary formation.
Absolutely.
A lot of work.
Wonderful field. If you're interested in this stuff and you got enough years left ahead of you, try to look into that.
And if you're interested in that thing or other areas of research or study, one of the things you can do, of course, is come to the University of North Dakota. And we have both online classes that you can take. And in fact, I'm going to be teaching an online astronomy class in the spring semester, 27. So if you're interested in that, I say a little bit more about that when we get closer to that time. But we have lots of classes, as I mentioned, both online and on campus. and for a variety of programs, not only in the STEM field, but other fields as well. And as an author, Robert, you love writing. So communicate. Exactly. Now, of course, what we do at the end of every podcast is we have a quote for you. And by the way, just to let you know ahead of time, so in case I forget it, don't forget our next podcast will be a week from today. So that's July the 7th, Tuesday, July 7th, I believe. Now, we always leave you with a quote at the end, but today I decided not to do that. And there's a serious reason why, is because one of our very early viewers of this podcast several years ago, when we first started, like I said, we'll be getting season 5 in January. So several years ago, we had a viewer who was really keen on watching the Cosmic Pie. And I heard a couple weeks ago, unfortunately, that he had passed away. Now, and the reason why I'm mentioning this is because if you have any issues, if you feel unwell from a mental point of view, please seek help. There's lots of people out there that can help you, but people need to know that you're suffering, that there's something wrong. And so please, if you're feeling down, if you're feeling depressed and it's more than usual, then please go talk to other people out there. So mental health is a big thing, of course, in society today, and we don't want to lose any more viewers. And
we don't want to lose anybody.
It's not worth it.
It's not.
And there is help out there. And hopefully, for those of you who know people that are struggling, please check in on them.
Yes.
Please check in on them. It really matters. So with that, thank you very much for watching, and we will see you next time.
Bye, folks.